Now I'd like to introduce chapter 6 and the idea of potential energy. So let's do a little thought experiment. So if I have a mass that I'm holding in my hand and I move it upwards with a constant velocity, right? So I'm exerting a force on it with my hand, and it is going upward with this constant velocity. The only way it can go upwards with a constant velocity is if I am giving it a force upward, because otherwise, if there was no force upward, it would accelerate downward, right? And in fact, for the velocity to be constant, my force of pushing it up has to be exactly the same as the force of gravity. So the fact that this velocity is constant, this is supposed to be my hand, by the way. This is like stick figure hand. Anyway, not, okay. So the fact that this is constant means our free body diagram has to look like this. mg down, and we can call this F external or F lift, maybe, I don't know, the hand lifting it up. And these two have to be equal if we're doing this at a constant velocity. So we have two forces on this. We are doing positive work, right? If this is going in the upward direction, right, the direction of motion is up, and the force we are exerting is up, we do some positive work, adding energy to the block. However, we know that if this is moving at constant velocity, the block is not changing its kinetic energy, so this energy must be going somewhere else, and that is gravity, which is giving it a force down. Gravity is doing negative work on it. Negative work, right? As we lift it up, gravity is pulling it down, so force down, direction of motion up, that's cosine of 180 degrees, so that gives us a minus sign. And negative work, of course, is taking energy away. The net result of this, if these forces are the same, is that the energy of our object stays the same, which is where we started because we move with constant velocity. Okay, so now doing negative work is something that forces like friction do also, right? We saw that if we, push the block across the surface, the friction opposes that direction of motion, and so if we move to the right and the force of friction is to the left, friction does negative work and that energy disappears. But something is different about gravity, right? If I lift this block up, so let's say I'm starting from some height, I lift it up, and I do positive work on it, gravity does negative work on it, and then I let go. Gravity now did positive work on it, right? I let it go, and it started moving down, which is in the same direction the force of gravity is pulling on it. So in other words, gravity did some negative work before. Gravity took some energy away from the object, and then when I let go, gravity gave some energy back to the object. So this is an important idea that gravity can borrow and give back energy. And it turns out we have a word for this kind of behavior. Gravity is a conservative force. And conservative force in this context means, yes, it can do negative work on something, but we can get that energy back. And in fact, we can get exactly that amount of energy back by letting gravity do work on it again. So we can get our energy back. This is not like friction. If we push the block this way across the table, friction does negative work, and then we let go, and the block does not snap back in the other direction, it just sits there. The energy is, for the purposes of this chapter, gone. All right, great. So how do we account for this energy stored in gravity? Well, it is directly related to the work done by gravity in this process. So let's talk about this energy stored by gravity. So this is called gravitational potential energy. Our variable for potential energy in general is a capital U. Sometimes in the spirit of accidentally sometimes writing KE for kinetic energy instead of K, I sometimes write PE for potential energy instead of U, so I will try not to do that. And since there are other kinds of potential energy, this is just gravitational potential energy, we're going to put a G subscript on that because we're going to learn about at least one other kind of potential energy very soon. So the potential energy of an object from this force of gravity, from the existence of gravity, is equal to mgy, where y is our y coordinate, the height of our object. So m and g, mass, gravitational acceleration, this part is just the force of gravity, right? And y here is just the height. So in other words, this really does look like a force times a distance. This is just how much work gravity is doing, but with a minus sign, right? So if I lift an object up, if I make y bigger, gravity has done negative work on it, right? So in fact, we can write that down. The work done by gravity is equal to minus delta UG. So if gravity does negative work, that is an increase in potential energy. If gravity does positive work, the object moving down, that is a decrease in potential energy and a consequential decrease in height. Because we often are going to talk about changes in the potential energy, we are most frequently going to use something like delta UG equals mg. Delta y, m and g aren't going to change, but our height is the thing that changes. So this is probably the most useful potential energy equation, but this is kind of the definition, so I'll put a box around that one. All right. So other things to say about this. We did learn in kinematics that what we use for our y variable is arbitrary, meaning that we can call any height y equals 0 and measure everything relative to that and still get the same answers that we would have otherwise. So what does that mean with the potential energy of gravity? Well, that kind of implies that since we can shift these y's around by any amount, that the actual value we have of the gravitational potential energy is kind of arbitrary. Well, that is true. You cannot say, for this object in this circumstance, its value of U is 10 joules, and that's the only possible answer. This is always measured relative to some height that we're calling height 0. And that's, that's okay, because again, we're looking at the changes in height of an object, just like in kinematics. So when we look at those changes in height, we will look at the changes in energy, and that will tell us how much energy is entering or leaving this potential energy. All right. Lastly, I want to remind you of this equation. So the work done by gravity is equal to negative the change in the potential energy. So this is going to be useful because when we have our work energy theorem, the work done by gravity might appear in there in the net work. And so we can replace that with a change in potential energy. Now that's not, practically speaking, that's not going to be a big change, since this is just a force times a height still. But we're going to be, talking and using about potential energy more, so that's a good thing to get used to. Okay, the actual last thing I wanted to say about gravitational potential energy is the following little example. So if I have, we won't use any numbers here, we'll just keep this conceptual. So if I have a ramp and I have a block that is going, up the ramp to some higher position, we know that the force of gravity is like this. The direction of motion is like this. So in ft cosine theta, we have some, ft cosine theta, to calculate the work done by gravity, we have some big angle here, right? So we're not going to get the full fg times the distance, it's just some fraction of that as determined by the trigonometry of this big angle. Okay, in in our potential energy equation, so that's the work, right? That's related to the work. In our potential energy only cares about the change in the height. So that is delta y of this object, right? How high it was at the beginning, how high it was at the top. The difference between those is delta y. So it seems like you could get two different answers from this, since these are two different ways of looking at this, right? F, force of gravity, times d times cosine theta for this big angle versus mg times delta y. Are these two things really the same? And I guess up to a minus sign, right? Because wg equals minus delta ug. And yes, it turns out this delta y is going to be exactly this d cosine theta. And you can convince yourself that this is true by drawing some triangles. I won't bother you, but I just wanted to say, whichever way we look at this is the same. We will get the same number, the same amount of energy leaving the block because of work, or leaving the block because it is becoming this potential energy.